So Rob, what's up, Jenny?
I don't know, when I do my stat calc,
Yeah.
and I want more stats,
Yeah.
I can't get rid of that?
Yeah, here, let's do this. Let's just turn your mode. We're gonna turn that stat wizard off. This wizard is a pain in the ass. There you go. Now when you
Won't
do
do
stat,
that anymore?
no, now it
Okay.
looks like ours.
Awesome.
Yeah, you got it. I don't know, that's a, they fixed something that didn't need fixing and they created an alternative problem, so.
Yeah.
So here's what I've got. Here's what I've got right here. I've got the L1s over there. My L5 is where my 2, 3, 4. And so what I'm going to do is I'm going to run stat calc 1var on L5 and L1. So this looks a little weird, and chances are you guys didn't have to do this, but because I already had the 2, 3, 4, 5 in L5, that's where my data is. And then my frequencies, or in this case relative frequencies, are in L1. And this should agree beautifully with what you guys got. This should agree beautifully with what you guys got, which means we have an average. We have an average of 7. But you guys knew that, didn't you? You guys knew that was going to happen because that's the center of the distribution. How would you describe this distribution if you had to use some words? If you had to use some words to describe this distribution, and you don't have to graph it, so I think it's pretty obvious what it looks like without having to graph it. If you had to use some words to describe this from back in the day, I say back in the day, I mean 2 weeks ago, what words would you use? What do you think? What do you think? I hear a vote for bell-shaped. We have a second for bell-shaped. We have a second for bell-shaped. Good. I like that. I like that. Any other words? What does bell-shaped imply?
Outliers?
Oh, it might have outliers. Good. It might have outliers. What's going to help us identify outliers, Robin? I love this. I love this. What's going to help us identify outliers? This is 7, and that's 2.4. What's going to help us? Please notice, friends, I'm calling this little sigma. Notice how there is no S up there? Almost as if the TI knows you're dealing with a population. I wish it was that smart. It's not. There's a mathematical reason. But that's the beauty. There's no sample. This is not a sample. This is everything that can possibly happen. Yes. Cool? Fair-ish? Okay, good. So, could we identify outliers using these values right here? If we think this is bell-shaped data, and I think it's fair enough to call it bell-shaped. I think it's fair enough to call it bell-shaped. I'm looking at some values up here. I'm going to throw this back up. I'm looking at this. Believe it or not, it's actually not bell-shaped. It's actually perfectly linear in an absolute value, and we'll come back to that momentarily. But if I look at the median is 7, as is the average. Checking for skew, that means there is 0 skew, which means there's no reason to think it's too skewed to not trust the average. So friends, using our little 2 standard deviations rule that somebody mentioned earlier, can we identify outliers this way? Can we identify outliers using 2 standard deviations? I think we can. So your typical values, whoops, that starts with a V. Your typical values are going to be within 2 standard deviations of average. So you're going to have mu average plus or minus 2 sigma. Now please remember, up till now we were calling mu x bar and sigma s, but that's because up until now what were we dealing with? What are x bar and s related to? Versus mu and sigma.
Oh, it's not the...
It's not it's a statistic, there was a sample.
Yeah.
Now, please notice your TI still calls this x bar. It's unfortunate. It's unfortunate. It still calls this x bar. So that's interchangeable with mu when you have a population. Just realize that. So yeah, the reason we were calling it x bar and s up till now was because we had sample data up till now. But now we've switched over. This is an entire population. This is everything that can happen when you throw a pair of dice. That's pretty rad. That's pretty rad. Now I apologize. I should have made a mention of this. The TI will never call the average mu. It always calls it x bar. But all you've got to do is look and see, oh look, there's no s. Therefore, this must be mu. That must be mu. I mean, it's basically telling you it's a population. Okay, let's do it. So mu plus or minus 2 sigma, well mu is 7. 2 sigmas is 4.8. If I take 4.8 away from 7, what do I get? Is that 4 point, carry the, was it a 2.2?
2.4. Oh, wait.
Oh, I'm rounding out to 2. I'm sorry, I rounded out to 2.4. So if I take 4.8 away from 7, the minus part, The minus
Oh,
part
okay.
is 2.2, and the plus part would be 11.8. You see what I'm doing here, friends? I rounded off the sigma to 2.4. Well, I rounded that off and then doubled it to give it 2 standard deviations.
I see.
Yeah, same thing as before, except I'm using a truncated value. So what this tells me is the typical rolls are going to be within 2.2 to 11.8. Do we have any atypical rolls then? Do we have any atypical rolls? That one right there, and that one right there. But couldn't we have identified those atypical rolls without doing all of this? I think Jada did it about 20 minutes ago. And how did she do that? Do you remember what you did, Jada?
No.
You can say no, it's totally fine. You did. What did you say about the ease of rolling a 2? And I put ease in quotes because rolling a 2 appears to be pretty difficult. It's a low probability. So one way we can identify outliers is what? Data points that are easy to get.
No.
Data points that are difficult to get or rarely seen. Rarely seen. So I like that as a third definition of an outlier. And it actually ties in beautifully to the ones you already know. Check the probabilities of events. If they are rare, if they don't happen very often, I'm putting a lot of quote marks in the air right now. If they don't happen very often, they're termed outliers. And here's a general rule for you guys to kind of think about. Here's a general rule for you guys to think about. One more way to ID outliers. One more way to ID an outlier. If the probability of some event comes in less than 5%, comes in at less than 5%, mathematically and statistically, that's generally termed an outlier. If something comes in at less than 5%, then that event is considered an outlier. Unusual, rare. So in other words, you can just look at the distribution of probabilities and say, oh, well, stuff should have happened here. It should have happened here, so the stuff that happened out here is weird. But when you say out here, how far out there do you have to get? Well, this gives you kind of a metric for that. Look at the chances. If they come in less than 5%, that happens rare, and it happens not enough to call it rare, to call it unusual. It tends to agree pretty well with this as long as you have the same exact data. So this is just a third, and I told you guys there are literally dozens of ways of IDing outliers. I don't want to get into any more of them. But this one is a way for probabilities. So you don't have to revert back to your box plot or your histogram. You can just simply look at the distribution. And that's why what Robin said about converting these things to decimals is so helpful. It's so very helpful because converting these to decimals, you see automatically, oh, less than 5, way less than 5%. 636 is like 17%. That happens pretty. Did you catch the 636? That's the same likelihood as all of these. So in other words, you see 7 as frequently on average as you see any of the single die outcomes. And then they just start falling away and falling away and falling away. And we put, it's somewhat arbitrary. The 5% is, why not 4%? Why not 3%? In 244, we'll deal with that question pretty much every day. But the 5% is well ingrained in standard practice for industry. Haley, go, please.
So 2 and 12 are the outliers?
By this rule, and also by this rule, yes.
Okay.
They are. Go ahead. What's concerning you?
So I just want to know why.
That, again, remember this. Outlier definitions are just that. They are defined to be this way.
Okay.
Human beings have said, we need a metric, we need some kind of a measurement.
Right.
So we're going to say anything less than 5% comes in as an outlier.
Okay. So the 136 is less than 2.2.
It's less than, well, it's less, well, the number 2 is less than 2.2.
Oh.
Because remember, good. I love what you're saying right here, Kelly. I love what you're saying. What she's saying is she's concerned about the number 2 versus the probability of 136. When you set this up statistically like this, it's the average sum and the standard deviation of the sums. So these numbers here are all sums on the dice. So these numbers are looking at this column.
Oh, okay.
Is that fair? And I realize now the camera's not looking at this, and I want to say that again, because this is very important, what you just pointed out, in case somebody uses this later.
Okay.
The average and the standard deviation are of the sums, which means this range is the typical values of the data. So when you look at 2.2 to 11.8, you're actually looking at the data in the X column. This definition of outlier over here simply looks at the probabilities, scans down this column, and says when they're too small, then these are outliers. So it's really depending on what you're using to make the call. Are you using the data to make the call, or the probability to make the call about the data?
Okay.
Great question, by the way. Thank you for that. Is that good? You guys buy that logic?
Yeah, that's
Good, cool. Now what I want you to see, and we're gonna let this run over break. I'm gonna come back here, and I'm gonna shut this down and switch over to you. I've got a little simulator here, and I've run it exactly 36 times. One for each of the theoretical outcomes of rolling a pair of dice. Do you see our distribution that's over there occurring here? It's starting to, isn't it? It's starting to. We've got a lot more happening in the middle than we do out on the sides. Now, we haven't had any snake eyes show up yet. That's to be expected. We should have some inconsistency. We also have too many 12s, according to the probabilities. According to the probability, we should have, we got just enough. We got 1 12. Down here, there's 2 pie charts. Why are there 2 pie charts down here? Why do you think there's 2 pie charts? 2 dice, each one for 1 die. Die number 1, die number 2. If I let this guy go, if I let this guy go and let him randomize, he catches up every once in a while up top. What are you beginning to notice first about these 2 pie charts down here? They're starting to do exactly what they're supposed to do. When I say exactly what they're supposed to do, they're beginning to become that perfect 1 6 1 6 1 6 1 6 1 6 and 1 6 beautifully. Now I didn't make a pie chart for this one up top because I didn't think it would be very, very sensible to make a pie chart for that many different outcomes, especially because I'm not sure how our minds would process 136 versus 336 and stuff like that. However, look what you're starting to see here. Now, I have to stop every once in a while because it's just, I think the graphics are just a little much for Excel to deal with. On my computer in my office, it works very, very quickly. But look at these numbers right here, friends. Look at these numbers right here. 136 is about 3%. That's what's coming up. About 3%. Roughly twice as big, 6%. Roughly twice as big. Roughly 3 times as big as this. It's not getting there yet, but it will get there the longer we let it play. So what you're beginning to see, actually, it's not a perfect bell curve. It's actually a perfect absolute value curve. It goes like this.
I was thinking about the stairs.
Very much so. Very much if you had it be stair step like this. Very much a staircase. Very much. But this side is exactly equal to this side. So what I encourage us to do right now is let's take 5 because you're getting that glazed look.
So symmetrical.
It's very symmetric. That's the word I was actually fishing for earlier. Nobody said it. I was fishing for symmetry. They're perfectly symmetric. But take 5. Let's let this thing run over break. Get 10,000 or 12,000 trials. Come back and see how it agrees with our theoretical curve over there. Then we'll play some more. Oh, it's rad.